Okay, so let's get started. So today I'll be talking about machine learning RDMs for molecular ground and excited electronic state. So, uh, so I'll start with a brief motivation behind my work. So standard quantum mechanical methods are still very costly if one wants to simulate realistic systems. And that's even true with the so-called mean field methods like Hartree-Fock theory or density functional theory, which scales as n to the power 4 or n to the power 3 with respect to the system size. So in our case, we aim to tackle that problem by building machine learning models. And in particular, what we aim to do, we want to learn the electronic structure rather than having different models for different properties. Now, what do we mean by electronic structure? So standard is basically, these are the three options which can essentially capture electronic structure for any particular system. So the first option is the wave function. So if you know the wave function of a system, you can compute the expectation value of any operator in this way. But wave function is a very complicated or complex quantity to learn. So the second option will be learning the electronic density. And due to the existence of rigorous theorems, you know that if you know the electronic density of a system, you theoretically have all the information of the system. But in practice, what you have access to the expectation value of all the multiplicative one electron operator. And then the third option is the one electron reduced density matrices, where also you have this rigorous theorem that exists in the electronic density. But for one RDM, if you know the gamma for a given system, you can compute the expectation value of any one electron operator. So that's why we have chosen one RDM as the central target quantity for our machine learning models over these wave function and electronic density. So now, how do we do it? So to build the machine learning models, we made use of the following rigorous mapping between the external potential, which is the nuclear electron attraction potential, and the gamma. And our goal of this work is to learn this mapping in such accuracy that the gamma that you are getting out of your ML models, it's kind of is indistinguishable that you get from standard electronic structure theory packages. And by doing that, we completely sidestep the typical SCF or post-SCF iterations of electronic structure theory methods. Okay, so now this is the workflow that we have used for building building our machine learning models. And the panel A is basically is our original model that already got published, and panel B is our recent addition to the recent addition of the optimization protocol to enhance the model performance. So as I have mentioned, so the target is to learn the mapping between this external potential and the one RDM. So what we do for a typical molecule, the machine learning workflow works like this. So for a given molecule, at first, we generate the training points using normal mode sampling. And for all those training points, what we do, we compute the external potential and one RDM in the GTO basis. And we use so for machine learning purpose, we use the features in these matrices as the input, and this is our output. And we call this like the gamma learning state. And what we have found is that the KRR, that is the kernel ridge regression, works best for this kind of mapping.
But sorry, these matrices, these colorful matrices, that's a representation of the gamma.
Yeah, so this is the discretized gamma in the GTO basis. Yeah,
they're color coded so that if it's darker, it's higher.
There's a contour.
I see. So I see. That's in the basis. I understand.
So you would have thought that we are done by just learning this map, but if your goal is to get the energies and forces of post-Hartree-Fock methods, then there is no way you can get to that by just learning one RDM. You need the two RDM information. But in this case, what we do, we actually set up a different map, which we call gamma plus delta learning. Even for so-called mean field methods, you can often the one RDM that you got from the gamma learning, it's not that accurate. So you can set up a different map to get access to the high quality one RDMs. And that you can use to compute the expectation value of one electron operator, mean field theory energies and forces. You can build quantum operator, compute the band gap. You can compute the.
And again, the training data comes.
So for
where-
training data,
Where do you get the reference gammas?
So the reference gamma coming from this, we are doing like a normal mode sampling. So we do a normal mode analysis, and we displace like we generate the structure by applying displacement along these normal modes.
But what gives you the gamma? Like some method, like some electron structure method.
Oh, so here, yeah. So that depends what you're interested in. So if you want to do like make a model for Hartree-Fock theory, you can use the Hartree-Fock gammas. If you want to do a post-Hartree-Fock very accurate FCI level of method, then you can use that. Yeah. So this is not required, but you can also set up a different map to learn the energies and forces of the midfield theory by setting up a different map. And so this whole thing is called gamma plus delta learning. And what you have found is the linear regression model workspace for this kind of mapping. Okay, so this optimization protocol that we have recently added, it's basically some addition of optimization procedures, which includes hyperparameter tuning, optimization of training set size, optimization of the kernel type. And by doing that, what we have found is that you can completely bypass the gamma plus delta learning step to get access to the high quality 1RD. Yeah.
Just one quick question. In your formula, there K is your potential matrix.
That's the kernel matrix.
This is the kind of matrix.
Yeah, so this is the kernel matrix, and the form of this depends on the kernel type that you're using. It can be a linear kernel, or it's a RDF kernel. It can be a polynomial kernel.
Okay, and what the kernel is going from from where to where? Sorry.
It's a real number,
Yes.
and you take two potentials, and you do something to these two potentials to get a real number. That's a kernel method.
It encodes the similarity between 2 points of those informations inside.
Imagine you take the integral of V and VI, like an overlap type, That's a number. That would be a linear kernel.
Yes.
VIs are your training
Input,
right?
yeah, training set.
And beta I are found through the inversion.
Yeah, like this.
Well, you never really do an inversion with solve a linear problem, but formally, yeah, you can write that.
Right. Yeah. I was a bit confused with the word kernel, but I was kind of used to compute, for example, dot products in a higher dimensional space.
Okay, so this is our machine learning workflow look like. And before I show you the results, so these are the notation I'm going to use. So, and I'll be mainly focusing on the results from DFT. So our electronic structure method is density function theory here. So DFT gamma is the ML model where you are using just the gamma learning step, and DFT gamma plus delta gamma where you are using the gamma plus delta learning step to use this high quality one RDM to compute the energy and forces. And this DFT ML is basically this, where you are actually setting up a different map to learn the energy and forces from the one RDM. Okay, so now how does our model look like? So at first we looked at the performance of our model in the energy predictions. So here I have shown you the RMST error or the error in the energy predictions as a function of training set size for these two small molecules with all these ML models. And if your goal is to achieve the chemical accuracy, which is typically 1 kcal per mole, you can get there by just using a few tens of training points for both this molecule. But in our case, we aim to achieve the typical SF threshold accuracy. And to reach there, you need probably a few thousands of training points.
What does SCF threshold mean?
So when you run a 34 calculations, so all these you have to solve those equations self-consistent, right? So SCF threshold means like the energy that you are getting out of is like 10 to the minus 6.
Oh, I see. So it's your
It's called for
Emergency.
numerical criteria for
tolerance or whatever.
Yeah.
Oh, I see. Okay.
Yeah. Yeah, so yeah, basically your digits, like energy that you are getting from here, it will be 6 digit after decimal, like similar compared to the actual QM calculations. Yeah. So then this green curve, which is our optimized model, we can get there faster compared to the other two models, even without the delta line step. We also looked at the extrapolation capabilities of our model. And to do that, we actually compute the homolumo gap by the machine learning predicted gamma. So we got the gamma from the machine learning prediction, and we do a single diagonalization by building the fog matrix to get the orbital energies. So what we looked at is basically we looked at the homolumo gap for these two molecules along some internal coordinates. And in these figures, these red histograms are the training point regime. And as you can see, both the ML models works pretty well, even far away from the training points. The accuracy of this optimized model, which is the orange curve, is much better compared to the actual model, like the original model. You have any questions?
Oh, sorry. Just
So then we looked at the accuracy of the force prediction from our model. And to do that, we have ran a bunch of AIMD trajectories using our reference method, which is the B3LIB, and AMD simulations using all the ML models. And for this molecule, we have run it. So on the panel A, I am comparing the performance of the gamma learning models with respect to the benchmark. As you can see, the dynamics from both of these models are more or less stable. However, the energies that you are getting out of it, it's not perfectly matching with the B3LIB energies after certain point of time. And we know that we already know that is because due to the inaccuracy of the forces, and we already have fixed it. So if you want to know more about it, you can talk about it later after the talk. So moving on to the ML models, where
sorry. So what you're doing there, you have a finite temperature,
Mhm.
and
this is the MV simulation.
yeah, so you give it some non-equilibrium and then just let it go.
Yeah, let it go and see how the energies look like compared to the reference.
You want the energy to remain constant on average, hopefully.
So that's not the total energy, that's the electronic
Electronic
energy. So it will oscillate. But the idea is that these are, in this case, three independent trajectories, but they all start from the same initial conditions.
Mm.
So if the three of them have this exactly the same energies and exactly the same forces, they should all produce the same electronic energy curves that will oscillate, yes? But you see that after some time, the orange one kind of decoheres from the other ones, as you would expect. They are all gonna decohere at some point. But the orange one decohered before because it's only 15,000 training points compared to the green one, which has 30,000 training points. So the green one is right on top. Right, so that's
a pretty stringent test.
yes, very stringent, yeah.
Yeah, but we have already found a way to like fix that also.
Yeah, even that can be fixed.
So because our ML models are not variational, the gamma that you are getting is not variational. So you have to do something with it, like to make some correction with the forces.
But we know how the kernel changes when you change the external potential, so we can actually compute a force correction due to the how the kernel change with the so with that correction, this all goes.
Okay. So moving on to the ML models, where you have a separate learning map to learn the energy and forces from the gamma. So there, if you see, the energies are more or less matching with the B3LIB benchmark. And that is because the addition of the data learning, it's kind of reduced some of the error that is getting generated from these models. And although these are ML models, but I want to remind you here is basically these ML models also have access to good gammas. So to test that, what we have done, we have taken out snapshots from this trajectory and we compute the energies using these two models. And as you can see that the energies are kind of matching. So we still have good gammas even with these ML models.
How much faster is ML calculation compared
That's the next. That's the next slide. Okay. So here I have shown you the computational cost associated with our ML models. So on the left, this is the training cost. On the right is the cost associated with running MD simulations. So on the left, I am plotting the number of training set size to achieve the statistical accuracy for all these molecules. And this is our optimized model, and this is our original model. As you can see, the number of training points required to achieve SCF accuracy is more or less lower compared to the actual model. And regarding the scaling, so we are actually plotting here the training set size scaled by the number of vibrational mode to the power 3. For smaller molecule, as you can see, like the number of training points scales as number of vibrational modes to the power 3. But for larger molecule, it doesn't scale badly anymore. Then we looked at the MD cost. So this is the cost for 10 dynamic steps. So if you can see that all these gamma learning models, those are kind of 1/5. So the cost associated with these kind of 1/5 the cost of the actual reference methods. And the ML models, where you have a separate map to learn the energy and forces from the gamma, those are free, but you still have access to good gammas with these models. Okay, so moving on to the excited state 1 RDMs. So we wanted to explore the same idea, like whether we can expand the scope of our machine learning model for excited states. And for excited states, we know that the like simulating photochemistry is also very computationally expensive, because for photochemical applications, you need more accurate and computationally expensive method to represent the electronic states. And if one wants to excite state dynamics, it involves running hundreds of trajectories with these complex, computationally expensive methods. So that makes the whole thing limited to very small system. So machine learning can certainly help. So to tackle that, we have followed the same protocol here, where like we are learning the targeting the excited state electronic structure for our machine learning models. And the two additional quantity that you are learning here is basically the 1 RDM for the excited states and the transition 1 RDM, both of them. And this is the protocol. This is how the protocol looks like. And the only thing that is different here is basically for a two-level system, along with this map, you also have to learn the map between the external potential to the gamma 1 and external potential to the gamma 0, 1. So here you have this gamma learning for building the map between gamma and the transition 1 RDM. But if you want to compute the energy and forces from this 1 RDM, you need to build a secondary learning step, because with 1 RDM you cannot get to the energy and forces for most of the for post Hartree-Fock methods. So we call that delta learning. So the final goal with this is basically to do ML-driven excited state dynamics. But right now, the results I will show you, there I am focusing basically in the equilibrium regime of the ground states. Okay, so now how does our model look like? So here I am plotting the error in the 1 RDM predictions for 3 states, S0, S1, and S2 for this formaldehyde molecule. And as you can see, the error for all of them is in the order of 10 so max error is in the order of 10⁻⁶, and mean error is just on top of 0. So the gamma that you are getting out of these ML models is kind of indistinguishable that you will get from reference CRST calculations. And these we can achieve by just using 50 training points, which is also very interesting. We also looked at the energy and forces.
So sorry, so the training data is that also from excited states?
Yes, you need to feed the.
You have to have excited state.
Yeah.
training data.
So in this case, CI singles and doubles.
Ah.
And you just take the first two states, the ground and the first excited state. Actually, he's got this two.
Yeah.
The first-
But right now I'm focusing on this area. But if you want to go here, you need to add more training points, additively, then that will be necessary for those. Then we also looked at the accuracy in the energy and forces predictions. Those are just very accurate. You can see the RMSE and max error, both these in the order of 10 to the minus 5 or 10 to the minus 6, which is exactly that we want. And we also looked at the transition 1 RDM. Here also, so this is the transition 1 RDM for the transition from S0 to S1 state. This is for S0 to S2 state. And here also the max error is in the order of 10 to the minus 6 or 10 to the minus 5, which is pretty accurate. And we also compute the transition dipole moment from it and compare it with respect to the reference. And those are also matching. So the final thing we have done with this is basically you also tested the extrapolation capabilities for these models. So to do that, what we did, we basically plot the energy of the S1, S2, and S3 state for this water molecule along the wave stretching. So the solid curve is the reference, which you obtained by using CIST. And as you can see, the machine learning model. So this histogram is basically the where your training point regime is. And as you can see, our machine learning model is not only working very well in this training point regime, it also has good extrapolation capabilities even outside the training point regime, even near the crossing. So it's learning the crossing also. So that's also very impressive. So to summarize my talk, I hope I'm able to show you that the 1RDMML models closely replicate reference methods for both ground and excited states. We can also learn transition 1RDM with good accuracy. And we are also working on to extend the scope of these 1RDMML models to condensed phase molecular systems with Valeria. And then the next thing with the excited state 1RDM, we want to push these ML models for excited states to do ML-driven excited state dynamics. And we are also working on the learning 2RDM, and Jessica is going to tell more about that. And at the end, I would like to acknowledge all my PRG group members. So Monica is there. And I'd like to thank my advisor, Professor Michele Pavanello, and all other people involved in this work. And finally, I'd like to thank you all. And if you have any questions.
Yeah, we can ask questions to the speaker.
I have another question.
Right. Sure.
So in density matrices have a property that's called nearsightedness, which means that it's a function of R and R prime. Right? And when the R and the R prime are very far apart from one another, the density matrix becomes exponentially small. It's called nearsightedness.
Right.
That's going to become relevant when you work in the condensed phase. So in extended or in periodic systems,
Okay.
that's a property. You might not see it that much in small molecules, but you might see it in larger systems. So what I'm curious about is two things. A, have you already kind of looked at I mean, I know you've represented it in terms of the Gaussian basis set, but if you represent it in real space,
right,
whether you see this nearsightedness already. And the second question is, if you do the training, machine learning, would that be something that you can impose, in other words, as a constraint to make sure that your machine learning algorithms obey this nearsightedness?
I think we still have not explored like learning the one RDM in the real space. That's
You guys are chemists, right?
yes.
So you don't do real space.
No, but
Are you
the
chemists? Are
Gaussian,
you chemists?
I'm a chemist.
Okay, sorry, I don't want to.
but the Gaussians kind of mimic real space because they're atom centered.
Yeah.
So there is, you do see the diagonal dominant feature of the RDM. So you do see that. Of course, then if you have a molecule like benzene, you get a loop, and so in the end you get like
Yeah.
elements at the edge, right? Because of a similar.
Right.
But I mean, in a periodic system,
Right, you don't see that.
it's really quite nice, and people have studied this very carefully. Also, they've shown that exponent. It's kind of an interesting behavior. It's exponential combined with a power law.
Okay.
This is a combined power law exponential.
Yeah, we can certainly impose something like that.
Even the uniform electron gas goes.
Yeah.
The case.
Electron gas. So it might be
Interesting to impose that constraint to the molecules, but I think for these molecules maybe it doesn't.
Molecules is
the molecules probably.
But one thing we can do is to learn functional groups. Then that's one way to exploit nearsightedness, right? Where you
And that will be also interesting for transferability and all.
you stitch pieces together, and then you learn maybe how the
Yeah,
non-additive part, if you wish, of the RDM, which is supposed to be small due to the nearsighted.
yeah, that will be very interesting. Yeah. Okay.
Okay,